Converse to Theorem 9 says to us that, remember, converse would be a reverse statement. So in this case, we're saying that the sides opposite equal angles of a triangle are equal. And we abbreviate that or write that in short to say sides opposite equal angles. So what are we saying here? We are saying here we start with a triangle that has equal angles. So we have a triangle that has equal angles. Now, when we have such a triangle, we then can conclude that the sides opposite those angles must be equal. The sides must be equal. Now, what are we saying here? We have a triangle here, CAR, and in this triangle, angle A and angle R, they are exactly the same. They are equal. That's what we know. And, in this theorem, we don't know what type of triangle we have here because we only know the angles that are equal. So we cannot really classify or identify this triangle. But what we know as a converse is that if you look at the sides that are opposite these angles, they must be equal. We conclude that these sides must be equal. And actually, by doing so, when I then say these two sides are equal, this then becomes an isosceles triangle. This then becomes an isosceles triangle because an isosceles triangle has a pair of sides that are equal. So it's exactly the reverse of what we were saying in Theorem 9 to say, you have here sides opposite equal angles, then you can conclude that the angles opposite equal sides. You start off with angles, then the sides that are opposite those angles must be the same, and therefore we can say this is an isosceles triangle because then now we just said the sides are equal. And for that reason, we can use this theorem if we want to prove that a triangle is an isosceles triangle. Because once you are able to find a pair of sides that are the same in a triangle, then we know that it's an isosceles triangle because by definition, an isosceles triangle is one that has two sides that are exactly the same in length.